Good morning dear students, myself Sachin S. Pawar and I welcome you to my third video on Unit 1 Solid States for PU2 Chemistry. In this video we shall discuss the arrangement of particles in space making a crystal lattice. Now when I say arrangement of particles, we will assume that particle as spheres. We will assume the particles as spheres. It may be an atom, ion or a molecule. Okay, so that will be considered as a sphere, and when I consider it as a sphere and I want to arrange those particles in a three-dimensional network, a three-dimension is the one which has got x-axis, y-axis and z-axis. So when I say three-dimensional arrangement of particles, we have to go step by step. First step is we arrange the particle in one dimension. We will get the edge of the crystal. Then second step is those edges need to be multiplied in one plane. You will get a two-dimensional arrangement, that is called formation of a plane of the crystal, and that plane is repeated many times one above the other, and you will get a three-dimensional arrangement of particle that is known as the entire crystal lattice. So as you see on your screen, there will be three steps. One step is packing in one dimension, packing in two dimension, packing in three dimension. I will short form it as 1D, 2D and 3D as it is there in your screen. So let's begin our today's session on arrangement of particles in space, that is called as closed packed structure. Closed packed structure. Okay. Now when I say closed packed structure, first we'll go for close packing in one dimension. So for this again I am taking one particle which is a sphere, and what I'll do is I'll just go on connecting those particles one by one. Okay, I'll just multiply these particles. Particle number 2 I'll just place it next to it. Particle number 3 I'll place next to it. I'll take fourth particle, place next to it, take next particle, place, and so on. You will form the edge of the crystal. You will form the edge of the crystal, and this is called as one-dimensional arrangement of particles. And whether it is a one-dimension, two-dimension or three-dimensional arrangement, you see every particle is in contact with some particles. Those become the neighboring particles. We have to count those neighboring particles, and for that in solids we use one word that is known as the coordination number. And if you just see, I'll use the arrow mark here, and you see every particle. If I just take say this particle, if I just take this particle, then you see, if I just take say I'll take this particle, then you see this particle is in contact with two neighbors. It is in contact with two neighbors. The neighbors are 1 and 2. That means the coordination number capital CN becomes 2 when we have close packing in one dimension. So in the edge of the crystal, the coordination number is 2. That is, every particle is in contact with two neighboring particles. With this, let's move on to the 2D arrangement. Now when I say 2D arrangement, I have to consider such edge and go on placing those edges one by one above the other, one above the other. Okay, so here in this case this is called as a formation of a lattice plane. Formation of a lattice plane. So we'll do this. There are two possibilities in which we can do it. What I can do is I'll just take that edge, I'll copy that, and such similar edges I can place it one below the other, one above the other, in such a way that the particles are aligned. This is one way of doing it. If the particles are aligned, so here you see the particles are aligned. The particles are aligned along x-axis and along y-axis. So they are aligned along two axes. So if you just see this arrangement, then this arrangement is referred to as square close packing. Detail about this we shall see in the next slide. One more possibility is that what I can do is I can place the next layer in between, in the second layer of particles. I can keep it in between the gap between the particles of first layer I can use, and the next layer of particle I can place it the next layer of particles I can place it in between, that means not aligned, I will place it in between. That is one more possibility. There is one more possibility. So this I will do it, and I will form 3 layers. I will form 3 layers, and you see this is one more kind of arrangement, and this arrangement is done in such a way that the particles of the second layer are placed in the gap between the particles of the first layer, and the process continues. Here the particles are not aligned, whereas in square close packing the particles are aligned in 2 axes. So the one which is there on the left hand side is referred to as square close packing, and the one which is there on the right hand side is called hexagonal close packing in 2 dimension. So this gives us a plane of the crystal lattice. So that is known as lattice plane. Let us see this one by one. Square close packing. Why it is called as square close packing? Again, you check out the coordination number. If you just check out the coordination number, you will see every particle is in contact with 4 neighboring particles. And if you just use an imaginary line and join those particles by an imaginary line, you will see a square. So it is called as square close packing. And since 4 particles are in contact with one particle, any one particle you choose, it is called as square close packing. And the coordination number of that should be 4, because 4 particles are in touch with one particle. If I take hexagonal close packing in 2 dimension, that is in the lattice plane, then you see each particle is in contact with 1, 2, 3, 4, 5 and 6 particles. And if I just join those centers of those neighboring particles by imaginary line, then you will get a pattern that is a hexagon. That's why it is called as hexagonal close packing, that is in 2 dimension. If you compare hexagonal close packing and if you just compare the hexagonal close packing and square close packing, you see in square close packing the gap between the particle is more, whereas in hexagonal close packing the gap between the particle is less. And therefore when I compare the efficiency of the packing, efficiency of the packing for square close packing and hexagonal close packing, since more number of particles are packed in less space in case of hexagonal close packing is supposed to be the best one. And square close packing is little bit less feasible, because the amount of gap between the particle is more. So in textbook what they have done is, in your syllabus what they have done is, they have continued the 3-dimensional arrangement only for hexagonal close packing, and we will continue the 3-dimensional arrangement in hexagonal close packing only. So this is hexagonal close packing. Coordination number is 6 particles are in contact with one another. Okay, now when I say hexagonal close packing, have a close look of hexagonal close packing. You will see one simple thing. So suppose for hexagonal close packing, we'll consider the particles of the plane 1. I will label it as A, and so on. And then you will see 2 types of gaps. We'll not use the word gap for this, we'll use the word void for this. So here if I take voids, then you will see there are 2 types of voids. One void is here between you see the 2 triangles, 3 particles forming a triangle, while consider 2 at the base and 1 at the top. This is one kind of void, I'll say it as a B. One more possibility is that 3 particles forming a triangle, where 2 particles are above and 1 particle is below. So here we will just separate those. We will separate those particles by some numbering, by naming. So we'll consider these voids or empty spaces as B, 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 and these empty spaces as C, C, C. So we have A particles, C voids, B voids, again A particles, C voids, A voids in a particular plane. Now when I want to go for a 3-dimensional arrangement, such planes I need to place above it. such planes I need to plate. So I have got one plane. So if I want a two-dimensional thing to be converted into a 3-dimension, just go on placing those planes one above the other, so that you will get the entire pattern, that is crystal lattice, in 3 dimension. So for this, if I just check, then there are 2 possibilities. I am going for hexagonal close packing. Since hexagonal close packing are there, the particles of the second layer need to be placed in the gaps between the particles of first layer, and there is only one possibility. Either you can place the particles on B voids, or you can place particles on C void. Just think, if I place the particle on C void, I can't place the particle on B void. I can show this. Okay, I can show this. See how I can show. Suppose I place the particle. Now this is the second layer of particle. I am just using a dotted particle, which is a transparent one. If I place one particle on C void of second layer, then the B void cannot be occupied. The B voids cannot be occupied. If I want, I'll just show you. Suppose I have a particle on B void. Second layer of particle on B void, then C void cannot be occupied. C void cannot be occupied in second layer. So we have an option. Either we can place the particles on C void or particles on B void. Since it is our what I can say convenience, we have labeled this as B and C. We will go with custom A, B, C, D and so on. So we will place the particles of second layer on the B voids of first layer. Particles of second layer, the dotted particles, we will place it on the particles of the B voids of the first layer. You see this kind of arrangement. So this is a formation of second layer. After formation of second layer, you see what kind of voids are created. If you just see those voids, then you see the void which is below B, highlighted as B, this void, and the void which is highlighted as C. These 2 voids are of different kinds. Void B is in contact with, just check, 3 particles of the first layer, that is A particles, and a particle of the second layer, and that's why 4 particles are there, and these 4 particles are a tetrahedral, form a void in between, the gap in between, that is called as tetrahedral void. Whereas the gap between the first layer and second layer, if you just concentrate on C particle, that is C void, then you will see the C void is in contact with 3 particles in the first layer and 3 particles in the second layer. This is referred to as, the void C is referred to as octahedral void, which is the void between the first layer and the second layer. Now the process of adding the layers need to be continued for getting the entire crystal lattice. So we will place now the third layer. Now when I want to place third layer, I have to choose whether I need to place the particle on tetrahedral voids, that is on B voids, or I need to place the particles on octahedral voids, that is C voids. If I place the particles on tetrahedral void, tetrahedral void of tetrahedral void is here, you see, tetrahedral void of the second layer, tetrahedral void between the first layer and second layer, then I cannot have a particle of third layer on void C, that is on the octahedral void. So I have to choose, either particle of third layer need to occupy the tetrahedral voids, or they need to occupy the octahedral voids. Only 2 possibilities, that is either B spot need to be filled or C spot need to be filled. Either B spot need to be filled or C spot need to be filled. So we'll continue that. So you see tetrahedral void, just give an idea. Tetrahedral void means 3 particles of one plane and 1 particle of the next plane. 4 particles are in contact with one another, and that is forming a tetrahedral structure. Therefore it is called as tetrahedral void, and it is called tetrahedral void. And if you see here, the tetrahedral void is B void. It is a B void. Tetrahedral void is a B void. Okay, so it is a B void. Tetrahedral void is a B void, whereas octahedral void is a C void. Octahedral void is a C void. Okay, so just see here, C void is octahedral void. 3 particles of second layer and 3 particles of the first layer, they are in contact, so this is an octahedral void. Okay, so I have octahedral void and tetrahedral void. Now third layer of particles need to be placed on either tetrahedral voids or octahedral voids, depending upon where you place the third layer of particles. Are you going to place the particles of third layer on the tetrahedral voids of first and second layer, or octahedral voids of first and second layer? That decides what kind of geometry you are going to get, and based on that we have got mainly 2 types of geometries. The first one is called as cubic close packing, referred to as CCP, or face centered cubic close packing, that is FCC. Here you see what is done. We have those A particles, we have those A particles, okay, those A particles in the first layer, the B particles in the second layer. Now when I want to occupy the third layer of particles on second layer, if you occupy octahedral voids, if you occupy the octahedral voids, this also I can show. Okay, so if I want to place the third layer of particles on octahedral voids, so now third layer of particles I am placing, the third layer of particles I am placing on B voids, that is on C voids. I am placing it on C voids. So let us place it on C voids. So I will place the first particle on C void, then the second particle on C void, and then third particle on C void, and so on and so on. You see, the tetrahedral voids cannot be occupied. Tetrahedral voids of the first and second layer cannot be occupied, and this kind of arrangement is referred to as, so I'll just go on continuing. I'll just place a few more particles. I'll place few more particles here. This is the third layer I am placing. Okay, so this is the third layer. So just see, on the octahedral voids, the third layer, the octahedral voids between the first layer and second layer, we are placing the third layer. So here this kind of arrangement will become what now? We have labeled the first layer particles as A particles. Obviously the particles of second layer are placed at position B. So A B arrangement, the first layer is A particles, second layer I will call it as B particles. Now third layer, you see the particles are placed at C position, therefore it should be called as ABC, ABC, ABC type of arrangement, and that arrangement appears to be like this, and the arrangement is here. You see, it is a face centered cubic close packing, because there will be corner for every unit cell, there will be 8 corner particles, and every face has got 1 particle at the center. That is the cubic close packing, CCP or FCC, that is face centered cubic close packing. So if you just think of any particle, what is the coordination number here? If I want to find out, then I can easily find out the coordination number here. For this, let me add few more particles here. Okay, I'll add few more particles. Right. Okay, so this is about the third structure, the third layer of particles I have arranged. Now if you just take any particle in second layer, just see it is in contact with how many layers. So if I just take say B particle, if I just take a B particle, then B particle is in contact with 1 B, second B, third B, fourth B, and one more will be coming here, one more will be coming here. So total 6 particles are in touch with B particle in its own layer, and that B particle, since it is an octahedral void, that B particle will be in contact with 3 particles of the third layer, 3 particles of the third layer, 3 particles of the third layer, and 3 particles of the first layer. That means total, if I just count the number of particles in touch, the neighbors, if I find out, a B particle, if that will be in contact with 6 particles of the same plane, 3 particles below the plane, 3 particles above the plane. So total makes it 6 plus 3, 6 plus 3 plus 3, that is 12. So coordination number in CCP or FCC is 12 here. CCP or FCC is 12 here. Let's move on to the next packing in 3 dimension. If I go for next packing, then I need to place now here in the earlier case in cubic close packing we have occupied tetrahedral voids. The third layer of particles are occupied by octahedral voids. The third layer of particles are occupied by the octahedral voids between the first and the second layer. So next choice is a third layer of particles can be placed. The third layer of particles can be placed on the tetrahedral void. On the tetrahedral void, we can place them on the tetrahedral void. So if I place on the tetrahedral void, just see what is happening. The arrangement, you see, tetrahedral void, below tetrahedral void of second layer. Okay, below the tetrahedral void, this is the this is C. So if I just go for B void, the B void is okay. So just see, this is the B void. So second particle is there. Okay, so we have B voids. Now when I place below the B voids, you see the particles are the particles of the first layer is coming. So when I place the particle of the third layer on the B void, then the particles of the first layer and the third layer gets aligned. So particles of first layer, if I label it as A, then the particles of third layer also need to be labeled as A. So the arrangement would be first layer A particles, second layer B particles, third layer again A particles, fourth layer again B particles, and the arrangement will be A, B, A, B, A, B type, and therefore hexagonal close packing, that is HCP in 3 dimension, is referred to as AB, AB, AB type arrangement. So this is regarding the hexagonal close packing in 3 dimension. So please note this. When I want to place, I will repeat again. When I want cubic close packing, then what I should do? I should place the particles of third layer on the second layer, making sure that the particles of the third layer are coming on the octahedral voids between the first layer and the second layer. Then it is called as cubic close packing. See, cubic close packing. Okay, and so I'll get the type ABC type of arrangement. ABC type of arrangement. And in this case, you see, the tetrahedral void is occupied. The particles of third layer are occupied on the tetrahedral voids between the first layer and second layer. You will get a hexagonal close packing. Again, here also, if you just keen in observing, then you will see each particle is in contact with 6 particles in its own plane, 3 particles behind it, 3 particles above it. So coordination number of HCP also becomes 12 only. So the comparison if I do CCP and FCC, hexagonal close packing, HCP, then if I compare this, then the first layer is formed, second layer is formed, third layer is formed, and so on. The process continues. So when you do this first layer, second layer, third layer, you will come to know that in cubic close packing, you see the third layer is generated using the void C, that is the octahedral voids between the particles between the first layer and the second layer, whereas in hexagonal close packing, the third layer particles are placed on the void A. That is AB type of arrangement I am going to get, and the arrangement is obtained by placing the particles of the third layer on the tetrahedral voids between the first and the second layer and that is called hexagonal close packing. So we have a cubic close packing and hexagonal close packing, and this completes the explanation regarding the formation of an entire crystal. We'll start with one sphere. Those sphere is arranged. Those spheres are arranged in 1D, that is, we form an edge of the crystal. That edge is continued in one plane. You will get the entire plane of the crystal. That plane is such many planes are placed one above the other, and we will get three-dimensional arrangement. One-dimensional arrangement, coordination number is 2. Two-dimensional arrangement, if it is square close packing, coordination number is 4. If it is hexagonal close packing, coordination number is 6. And again, if I go for three-dimensional arrangement, then depending upon which void of second layer is been occupied by the particles of the third layer, we have CCP and FCP. CCP is also called as FCC. That's it. That is the arrangement of particles, giving you the entire three-dimensional network to be known as close packed structure. So this is all for today's class. In the next class, we shall see more regarding the tetrahedral voids and octahedral voids. Thank you. I'll stop here.